Advanced topics in Python. To be honest, friends, I had a difficult time choosing which two topics to cover in this nugget. There are so many other ones. Regular expressions is a topic that comes to my mind that bear time. However, because we can cover only so much in this Introduction to Programming with Python series, I've settled on two function-related advanced topics that can really make your Python programs more flexible, dynamic, and better performing. The first of those is the generator function. As we're going to learn, a generator function is a kind of resumable function that instead of running through an iterable just all at once and returning a single object, we can actually stop and resume. In other words, save state in a function's execution. Generators are pretty cool. The second advanced topic we're going to look at in this nugget is the decorator. Decorators are functions that you can use to wrap other functions in. Now, I know that sounds pretty esoteric. Actually, it is. Decorators tend to be one of those advanced Python topics that scares off a lot of would-be Pythonistas. I'm going to take things slow and easy, though. Let's get started. As previously stated, a generator is a resumable function. Therefore, a generator function is going to return results one at a time instead of just giving you the function result as a whole. Now, generator functions are used almost exclusively in looping constructs. For instance, the for loop. Now, why would you care about a resumable function or a generator? What's the purpose? The main reason why Python programmers like using generator objects for their for loops or their iterations is that you can save memory. Instead of running a straight-ahead iteration, which brings back all objects in a particular range, let's say, or list, you know how iterables work, we can conserve memory by using the yield statement and suspend and resume the state of that function. So in other words, we can go through an iterable sequence to a certain point, yield that result, come back later, and pick up where we left off. Isn't that great? Now, generators work with functions as well as expressions. We're going to do a little mini review on list comprehensions. You'll remember what list comps are. List comps give us a list from an iterable sequence using for. Generator expressions are pretty much the same things as list comps, but instead of spitting back an entire list, which again can increase your memory footprint of your application, as well as consume unnecessary CPU cycles, with a generator expression, also called a genexp, we can return results on demand instead of, as I said, a full list. To sum up, generators are good at optimizing performance of your program and minimizing memory footprint for those iterable sequences. Let's now have a look at a generator function. We'll look at the syntax. Now, if it weren't for this yield keyword, this gen square function, which is a function that simply takes a range as its iterable and comes back with the square or the power of 2 of that input parameter or argument. If it weren't for the yield, then this would just be a standard iterator, wouldn't it? Remember, an iterable is any data object that can be iterated through or cycled through one member at a time. You'll recall that strings are iterables, lists, dictionaries, tuples, and also some built-in functions like range are iterables. So the way gen square works is we have a single argument that comes in that provides the topmost element in our range. We're going to use for to cycle through one at a time all the elements or members in that range up to n. And because we're yielding a generator rather than just a straight ahead data object, we're going to invoke the yield statement. So therefore, we could then assign gen square 6 to the name A, and A is going to be not a list, not a tuple, it's going to be a generator object. And I'll show you that in the demo in just a moment. Thing that's crucial to understand is that when you're using generators, you can then manually invoke the next member of that iterable sequence. So in other words, if we do next A, it's going to give us the very first value of for I in range 6, which would be 0. So 0 to the second power is 0. I'm telling you that the first time you invoke the next function passing in A, you're going to get 0 as your result. And then if you wanted the next member, you would just do another next A all the way until you reach an iteration error. Eventually, once you reach the top of your range, you're going to get a traceback. And in order to handle this in your code so that the program doesn't abort, you would simply run try and except and catch that error that you get when you finish. It's called the stop iteration message. Now this next function is important just from an architectural standpoint, because if we were not using yield and therefore we were just doing a straight iteration instead of a generator function, next is automatically invoked when you run the function. Yield simply gives us as the programmer flexibility and control stepwise over the processing of that iteration by means of, as I said, the next function. Now let's get into the interpreter and I'll show you how this works in Technicolor. Alrighty then, here we are in idle, and I'm going to start off pretty much duplicating what you saw on the whiteboard. We're going to define a function called GenSQ that takes one argument, n, and we're going to run our iteration for I in range n. Here comes the generator keyword, yield, and in this case, I to the second power. Now, normally in a function that's just going to do this in a non-resumable fashion, we wouldn't use yield, we would use, do you know, the return statement to return a value out of a function. A little bit of review from earlier in the course. So let's hit enter twice to get back to our Python prompt, and now I'm going to set the value of arbitrary name called a to a run of the gen square function, and I'll pass in 4 as my argument. Now if I just echo back a, you notice that it comes back as a generator object. Same thing if we run type A. Now you're wondering, okay, well how can we start to pull data from this function? As I said, we can do this one element at a time by using the next function. So if we're passing in 4, remember, we're starting our range with 0 and working our way up. Eventually, when we reach the top of the list and go beyond the range, we get a traceback, and the error that we're looking to catch here is stop iteration. So I think that pretty well shows you how generator functions work. Pretty nice stuff. Just by way of contrast, let me create just a standard iteration function. We're going to call this one ITSQ, IT square, for iterator square. Again, it's going to take one argument. We'll do things a little different here. We need to catch our result. So what we'll do is create an empty list and then simply append to that list the results of a for loop. So we'll do for I in range n, and we'll call the append method on the result object, I to the second power. And then I'll backspace back a level because we need to use return now to get result out of the function. Alright, 2 strokes of enter and we're back. This time my name is going to be B, and I'm just going to pop in 4 just like we did before, this time into the IT square function. If we echo back B, look what's happening. We just get the whole result of the iteration in one shot. And you know just by those square brackets what type B is, don't you? Let's finish our consideration of generators by now looking at generator expressions. A generator expression is directly analogous to something we've learned about earlier in the course, the list comprehension. Just by way of review, remember that a list comprehension or a list comp is a data structure that looks like a list, that's because it is, remember the square brackets, that represents a shorthand notation for building a list through an iteration. So our example here, we define a name called LC. We're specifying an operation, I to the second power, for I in, and then in this example I'm doing range 10, but you could also have any other iterable assigned to a name, let's say, or whatever, and you would just swap that in here. Range just serves as a really nice grist for the purposes of our example. And you'll note that if we echo back the object or the value associated with LC, of course it's a list that matches this sequence. Range to 10, take the square of each value, working your way up. The analogous way to go with generators is to use a generator expression. Now syntactically it's just about the same as a list comprehension, but notice that we're using parentheses instead of the square brackets. You know what a paren is, right? A paren always lets us know that we're dealing with a tuple object. So in this example, we're creating a name called gx, and in our parentheses, it's essentially the very same operation, isn't it? I to the second power, or I squared, for I in, and then here I'm using the range notation where instead of just giving the topmost value, I'm providing the initial value and the top value. It's up to you which of those notations you want. Now notice what happens if we echo back the value of gx. Again, it's a generator object. So you guessed it, we can use the next function to retrieve those results one at a time, or we could just do a for loop and bring them back all at once. It's up to you. But remember that generators in general are known for being really conservative in their memory footprint. It's sort of like a garden hose where a list comprehension is just turning it on and the water comes shooting out. Whereas with a generator function or generator expression, it's like you have a handle or a nozzle on that hose where you can control the flow of that stream. To demonstrate generator expressions, we're first going to contrast them with list comprehension. So let me create a simple list comp. That again is very similar to what we did in the whiteboard. Here I'm going to take 2 to the I power for I in range 15. And of course syntax error. Those are the easiest errors to catch, right? At least in most cases in Python they are. I was missing the assignment operator. So if we echo back LC, we get our list object. We already know it is of the list data type. All is well and good. There's the list comprehension. Now, to turn our attention to generator expressions, how can we do that? In this example, I'm going to build a simple list that'll serve as our iterable sequence. All right. And then for our genexp, I'm actually going to call this genxp. Remember, we use parens instead of square brackets. We're going to do an I for I in ML if I is greater than 10. So we're going to run through ML, gather just the data value. We're not going to square it. We're not going to do anything like that. We're just going to get the raw value. But our condition here is a little different. We're only looking for values that are above 10. So we're expecting to see 16, 32, and 64 here, aren't we? As expected, genxp returns a generator object. Same with print. So to get data out of this, of course, we can go a couple of different ways. We can invoke next, passing in genxp, 16, next, genxp, there's the 32, next, genxp, there's 64, and you know what's going to happen now, right? We get our stop iteration. Now, if we want to bring back all of them, we can still do that. We'll just invoke another loop. For j and genxp, give us j. One more time with feeling and spelling the name correctly. Now what we're seeing here, friends, is a failure in this for loop, and the reason for this is known and documented. Generators can't be rewound or reset. You'll recall that we used the next here to go through that sequence based on our generator expression, genexp. But once we've gone through the sequence, we've pretty much expended it. So what I'm going to need to do is redefine genexp and now try our for loop again. Let's try for k in genxp, print k. And there we go. Now if we try this again, because the generators can't be rewound, we've got this problem again. Decorators. As I said at the beginning of this nugget, decorators tend to confuse many Python programmers, even some with a significant amount of experience. However, when we look at it from a high-level overview, I really don't think they're that confusing. The first thing I want you to know about decorator functions is that we need to differentiate these from the decorator design pattern. Remember when we talked about object-oriented programming a little bit earlier in this training, I mentioned that OOP programmers have settled on a handful of well-known, well-trod design patterns that can prove really beneficial for application design. And there is a design pattern called decorator, but this is something a little different. This is a specific function type in Python that we could call a wrapper function. A decorator is a function that takes another function as its argument. Now what do I mean and why would we use this? Let's look at this really great example that I got from stackoverflow.com. If you haven't joined Stack Overflow, please do so. It's free and you can learn so much from the smart people there and even contribute your own knowledge. At any rate, what's happening here is that we have two functions, one called make bold, the second called make italic. And basically what this person wanted to do is find a way where it would be convenient to, in another function, take some string data, let's say, and as an as-needed thing, wrap that data in one or more HTML tags. Now, number one, this example is in Python 2, so we have to keep that in mind. And number two, I want you to see, if you've done HTML or XHTML programming, the B and I tag are pretty much gone the way of the dodo. But ignore that for a moment. Therefore, the make bold simply contains a return statement that wraps whatever your argument is in the B tag and returns that out of the function. Make italic does the same thing. It grabs your argument and wraps it in I tags. That's not the main point of the decorator. What's awesome is we can reuse the make italic and make bold functions whenever we want to either bold, italic, or both some text or some data. The way you invoke a decorator function is to use the name of the function, prepend it with the @ sign, and sit it right on top of the target function definition. So at the bottom of the sample code, you see we have a function called hello that returns a static string, hello world. Because we're decorating it, so to speak, with both make bold and make italic, if we then print out hello, it's going to give us hello world wrapped in both of those tags. Therefore, decorators provide a really convenient way to mark up code by wrapping functions. You'll see down here that the procedure of implementing decorator functions with this @ syntax is an abstract shorthand that really what you're doing is that you're taking the make bold function and passing in the hello function as its argument. Same thing for make italic. You're invoking or calling the make italic function and passing in hello to it. That is the bottom line with the decorator. There's nothing more to it than that. We're doing decorators in this final demo. Decorators, by the way, are an example of what's called metaprogramming. Wikipedia defines metaprogramming as the writing of computer programs that write or manipulate other programs or themselves as their data, or that do part of the work at compile time that would otherwise be done at runtime. And that makes sense because we noticed from our previous discussions of decorators that decorators are functions that accept other functions as arguments. I guess we could say that decorators constitute one of Python's functional programming aspects. Without further ado, let's get rocking. We're going to start by creating a function called 8times. I'm just going to abbreviate it to ET, and it's going to take a single argument that I'll call myfunc. What this function is going to do, it's actually going to contain an inner function and return that inner function. It's going to take an arbitrary number of arguments. You remember star args, I hope. This means we could execute the function with 0, 1, or more than one argument. And in this inner function, we're going to run for I in range 8, take myfunc, and then again, star args is a nice placeholder if you want your function to work with or without arguments. We're going to return inner function from ET function. All right, good deal. So this function is going to be our decorator. It's going to take another function as its argument and simply echo the contents of that function 8 times. I know it's kind of a contrived example, but it's better than nothing, right? Let's declare, just for the sake of convenience, a function called nondec. We'll call it nondec1 that has no arguments that prints out eggs. When we run the function, we get the result. No big surprise. Let's now add a decorator with @et to an identical function that I'll call dec1, and this one is going to print spam. When we run dec1, notice what happened. The function itself prints out spam once, but because we attached the decorator function et ran an iteration in its inner function using the passed-in function as its argument. Advanced Topics Review. You've really come a long way in this training. By the time you're handling things like generators and decorators, you have the vast majority of the Python programming language under your belt, and you really ought to give yourself a hearty congratulations. In this nugget, we examined generators, which manifest themselves as two types, you'll remember, generators and functions, as well as generator expressions, that use the yield statement to give us as Python programmers complete control over iteration. We then looked at decorators, which similarly, it always makes me think of my mother, who spent quite a bit of her time as my twin sister and I were growing up in Syracuse, New York, baking and decorating cakes, ice cream and regular traditional baked cakes. This, for some reason, is invoked when I think of the decorator. The decorator function allows us to mark up other functions by using a really convenient shorthand syntax. I hope that this has been informative for you, and I'd like to thank you for viewing.